It makes sense why that one guy, why it didn't work. Apparently a semi pulled out from a side road and it couldn't see the trailer. Yeah, he basically ran into the trailer or hit their back wheels. I don't know, but kind of scary. Oh, that's not 11.5, it's 11.15, sorry. So yeah, I would be all for, I'd change my thinking on that 180 degrees immediately because it would cause less emissions. So I would be for that. Okay, so 11.15, example 11.15, it says we've got a 3/4 inch diameter hole drilled on the center line of a flat steel bar as shown in figure 11.15. Now, I don't know, do I have that in there? Let me check here real quick. If that's going to be right there. Okay, and we'll copy that. And we'll put that right here. So, that steel bar right there. Okay, so this will, hopefully this will calm your nerves, okay? If we do this problem. I think it will. So, we've got that steel, well, let's see where we're at. The bar is subjected to a tensile load of 4,000 pounds, and they're showing that there. I probably shouldn't have made that so small. 4,000 pound load there, right? Calculate the average stress in the plane of the reduced cross section and the maximum tensile stress immediately adjacent to the hole. All right? So it's 3/4 inch diameter hole. And note here that they go ahead and do for you that R equals 0.375. So R equals 0.375. And we need to know what D is, don't we? Because it's R divided by D. We have to find that first, and then we can go and look for the K value. All right? So what do we do for D? Well, look, this says D divided by 2. D divided by, that's lowercase d. So it's the uppercase D minus D gives us the net area, doesn't it? Make sense? So if we take the 2.5 minus, well, what is that? Minus the 3/4. No, now be careful. 3/8 is R. The lowercase d is the diameter of this hole.
Oh, just 3/4.
Okay, 0.75. And we end up with what, 1.75, is it? Yeah, 1.75.
I don't think the
Square inches.
lowercase d represents the diameter of that hole. I think it's supposed to represent
The leftover.
the distance with the hole removed. Because I mean,
Yeah, that's true.
that's how
Yeah.
that's d over 2. Each of those.
But to
are d
find
over
that, but let's, well, equals D. Okay, yeah, the 0.75 is just, and let's get rid of this, I guess we better, minus,
What are we calling that?
well, we're going to call that, see, there is no, how about just the diameter symbol equals D. And I don't know why they show D divided by 2 there. I do, but you don't need D divided by 2. You just need D. I guess that's showing that it's symmetrical would be the only thing for that.
But it says it's in the center.
Right. Yeah. All you need is the resultant, the lowercase d, which is the leftover, if you will, after your hole, or in the case of your notch, or in the case of it's the smaller diameter after you neck that down.
Now, if the hole wasn't in the center, would that change things?
Well, would it?
I mean,
Still the same area, isn't it?
A surface
area.
No, it's still the same area.
But then wouldn't one side technically be weaker?
One side would be weaker, but if the pull was from the same spot all the time, you wouldn't have an issue. Now, if the pull was going off at an angle or something, you might have an issue if it weren't equal.
We're looking at the whole cross section.
Right. Yeah, and you're pulling straight up on it. If you start pulling it at an angle, if you had a small, let's say this side over here was smaller, didn't have as much thickness, and you were pulling that way, don't you think that would tend to fail first? Once that goes, then you could have a cascading effect where it would just keep ripping. So that would kind of suck. Okay, if this, then that. So don't get that confused with this problem though.
Well, I have another quick question. Since
Okay.
we went on that hand real quick. Now, let's say the bottom where it was pulling, it was strapped down. It was pulling at the 180-degree angle of that. Would
No.
that create basically the same up and down effect?
Now say it again.
Now, if you had both, you know how you had the angle off to 45, and let's say you have the 180 degree of that, still in the same spot, would it create this effect still?
If you had this one going this way
Yeah,
and this one going that way,
right.
so kind of like a couple.
Yeah.
I mean, if this side were smaller, then I don't know. I think this is going to want to make that rip, but it's not going to, this one down here is not going to affect that one. It sure wouldn't help matters, but that's essentially what's going to be happening anyway, isn't it? So
Yeah.
I don't think that's going to add on to it. Yes, sir?
That big symbol B represents the diameter of a circle, small circle.
This right here,
Yes.
this is the diameter of the hole. Let's say,
Oh, well, that means I said that is small circle.
yeah, that's the diameter of the hole.
Humanity G, then they subtract that fee, they subtract that fee from the whole, and they represent that by G by 2. It's going to be by 2.
I'm not catching what you're saying.
Yeah, diameter of a hole, and then small d, lowercase d by 2, both sides of the hole, lowercase d by 2, yes?
This would, so in other words, this right here
Yes.
would be 1.75 divided by 2. This side would be, and then this side would be half of 1 3/4. So let's see, what is that? Half of 1 is a half of 3/4 is 3/8, so 0.875 on this side, 0.875 on that side. Okay, and that's just showing you that it's symmetrical. Essentially is what's going on there.
And there's also no way to label the small d in the diagram straight across because there's a hole right. The only way
Yeah.
to label that dimension is by splitting it into two.
Right. But you have to realize you want all of it. You want the whole lowercase d, not just half of it. Okay? So yeah, that's how they have to show it in that case, but really all you're concerned, don't divide by 2. There's no real need to do that. Then you just have to multiply by 2 again. So don't get hung up on that. So then D is 1.75, R is 0.375. So R over D, okay, 0.375 divided by 1.75 equals 0.214, isn't it? So then we take that and we go up to this chart. Now, you find for me on this lower line here, on the x-axis, you find for me 2.1 or 0.214. That's what I'm saying. It's not an exact thing there, is it? So beware. But what you have to do, okay, you know this is 0.2, that's 0.3, so this must be 0.25, right? So we need 0.214. So somewhere along there, huh? maybe, something like that. Close as I can get with my marker. So you follow that up until you get to the curve that matches the diagram at the top. Which one of these curves matches what we're looking at on our problem? And it's this one right here, right? Now, it's interesting. They leave that as an A, a B, and a C, and then they make this 1, 2, and 3. But at least they did put circular hole, semicircle, and then fill it. So right there, somewhere right about there is where we're going to be looking for the K value. So then we come back across this way. Somewhere there close. What the book says in the example is that they're going to use a K value of 2.3. You know, maybe, I think we're close enough if we go, you know, to the first decimal place to the right. You know, if you'd say 2.32, you might even be getting to a point where it really doesn't make that much difference in the amount of force you're getting on it, or in this case, stress. So they use a 2.3. So now, that's the hard part. So it was, the formula was the stress max, right, equals the K value times the force over the area net, and that's what that lowercase d is, isn't it? Okay. Excuse me. No, that's not an area. You're right. I better erase that real quick. I'll have to get that out of my video, huh? Well, no, this is square. So, no, don't make it too difficult. Okay. So, note the area. Well, but you do use the D value. The area of that, the A net, equals the 1.75. Okay. Times what? It's 1.75 this way. Do they tell us what that number is in the problem? Oh, we're looking at the, well, that's how much you're,
So 80 at 1.75, 1.375.
right, but that's the net cross-sectional area of the plane of the reduced cross-section. Interesting. It doesn't. Oh, okay, I see it now. I couldn't figure out. It's like, no, where's that coming? Here it is, right here, hiding in the. It's 3/8 thick. It's like, nah, that can't. It couldn't have been tied to this number. Why did they have to use 3/8? Yeah, I was looking for the two sides, and I wasn't getting them. This is 2.5, but this is 3/8.
Yeah,
it's
it
like,
looks like it's almost a square.
and now you start seeing this radius. It's like, there's no way you're talking about the hole. It's the 3/8 thickness of the bar, right? Had to look at that pretty long. That value comes out to be what? 0.656 square inches, because that's the net area. That's the total area minus the hole, right? Okay, then that turns out to be, we were given that it's 4,000 pounds, right? Divided by 0.656 square inches. And so that's going to come out as pounds per square inch. whatever that number comes out to be, does it come out to be about, the average stress is, yeah, 6,100. I put the max there, didn't I?
You the K value.
Do what?
Value of K value. Value of K.
That's like 2.3 now.
The K value, oh, let's see, yeah, I gotta put that in there yet. Point, what, 2.1,
Oh, no, 2.3.
2.3, sorry about that. Yeah, had it here. 2.3 times that value right there.
Book confused you because they didn't put it in, they did it in two separate steps.
Yeah,
Yeah.
well, that is the max then.
Yeah.
Yeah, well, then that's wrong.
That's the 6,100 is right for the P divided by age.
Right, but
Yeah, but it's not the max.
right. I was showing the max. I wasn't doing the in-between thing there because that's what we were talking about.
Exactly.
14,030.
And that's the max that it's actually feeling due to that force, right?
Right. Now, the average, see, so the average, that's the max, and that's based on that hole being in there, right? If you look at the one right above it, in the example, what is that? Notice they're just doing the 4,000 divided by the 0.656. That's if you don't have the hole in it. It's what, 6,100? If there's no hole, so we'll put there,
That A net was calculated with the hole taken out of it.
huh? That's with the hole being drilled in it.
Right, yeah,
Yeah.
that's with,
Yeah.
that's including the hole.
Right. This,
Accounting for the hole.
let's say, with the hole, okay? And this one is without, so in other words, this 6,100 PSI, if there were no hole drilled in that, or if you looked, let's say you were looking at this cross section right here, there would be 6,100, wouldn't there? But then when you get down to here, what?
Your .656 on the bottom is still your A
Oh,
net,
it
which
sure is. Yeah, that's correct. So that would have to be, yeah, if I was doing up in here, it would be 1.75 times the 2.5 times the 3/8, wouldn't it? Yeah. So what is that average then? That should be, yeah, I don't know why you would even want that. To be honest with you, I do not know why you would worry about that number.
It would
I
be
think they
like
were just
maybe
trying to
the
break it down
average
for you,
stress
show you
distributed
the order of
across.
operations or
I
something.
guess the only thing I can think there is if you weren't accounting for that stress concentration, you would think it was only 6,100. In reality, it's 14,000. That is the only thing I can see there because you're not accounting for that stress concentration here, or in this one, you're not accounting for it. So you would think that it was 6,100 PSI, when in reality, it's not.
Why would they put that in the book? That's just confusing.
Would that be the average stress across that whole cross section, and then the max stress would be where it's concentrated near the hole? The stress is concentrated near where the hole is taken out.
So in other words, well, the average would be over this whole. Yeah, and I think if we look back, so everything, that whole piece right there, right, is what you're saying, and the
Yeah, 'cause the
14,000.
stress would be different closer to the hole than
Right.
it would farther away from the hole.
Right,
So
it's like a
average all
graduated
out.
type situation. So the average is 6,100, But right at that place where it's going through the center line, 14,000.
K is just a scalar.
Do what?
K is just a scalar constant. It's just it's increasing the stress at that point.
And let's see if we've got that. There's an illustration right here. That's it right there. Is that what you're talking about? Let's see. Get my there we go.
Based on a ratio
Yeah.
of the actual size of the amount of material that's been removed. So it's just scaling a proportion of that stress at that point.
Well, that's not very clear, is it? Yeah, is that does say the average, I think, doesn't it?
Yeah.
Yeah. Tensile stress average would be the, well, actually, it's the way they're showing it, it's not right at the, it's because of that being on that slope, it's somewhere out in there. But right here, it should be that should be the max right there. Okay, and that makes sense, doesn't it? Because you've got more material right out in here. So then they're taking the average of all of that area there, if you will. Personally, I'm not worried about that one. That's not where it's going to fail using this number. The max shear, the max stress is what you need. You need that number right there. Because right at the center line of that hole is where that's going to fail. So I don't know. This one doesn't. You may have to calculate it in some of your problems on the homework, but this one right here, is the one you've got to have. Max shear. That's the worst case scenario. And that's what we designed for in it. That's what sucks about our life. You have to look at everything. What's the worst case scenario? It does change your way of thinking. I will tell you that. Whether you like it or not. Or whether, in my case, whether my wife likes it or not. So that's what you got on that one. Now let's look at another problem. Example problem 11:16. Well, are we okay on that one before we move on?
The average is included either way. Whether you split it out or not, you still have it there.
Yeah, I feel like he almost did it just to show you the order of operations in the problem.
Yeah, if you take the K value off, you've got the average.
Right.
So,
Right. Yeah. I just don't see much need for that average personally. I see much more need for the max, because that's